You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. James Beacham. Dr. Beacham is a particle physicist, science storyteller, and filmmaker. He's currently a full-time researcher working on the Large Hadron Collider, currently with the Atlas Group of Duke University, based full-time at CERN. He received his PhD at New York University, and before that attended UC Santa Cruz, where he completed a double major in physics and math. His research focuses on searches for new particles and phenomena such as dark matter, dark photons, quantum black holes, and exotic Higgs bosons. He also advocates for future physics experiments such as larger colliders to address the biggest open questions in science. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. James Beacham, welcome to the program.
Thanks very much for having me.
Now, Doctor, you work with perhaps the most fascinating and largest scientific experiment that we are currently doing, CERN and colliding particles. And one of the major discoveries was the Higgs boson, which had been hypothesized since the 1960s, Peter Higgs. And this in turn points us towards the Higgs field. What is the importance of that?
Oh, that's a mouthful. Starting right out of the gate with an extremely good question. Well, yeah, first of all, thanks for having me here. And I'm always more than happy to talk at length about the stuff that we do at CERN. As you mentioned, this experiment, the one you're talking about, the largest experiment in human history, is called the Large Hadron Collider, right? And this thing that we, like you pointed out, that we discovered back in 2012 was this thing called the Higgs boson, right? And as you pointed out, these are some words that mean some things, and it's probably worth unpacking a little bit of what they mean. So the Higgs, of course, as you pointed out, first, this guy named Peter Higgs, who was one of about, 5 or 6 people back in the 60s who predicted the existence of this particle. But at the time, it was a bit of a weird oddball prediction, to be honest. It's something that, for all of its importance now and its prominence in physics as a discovery, at the time, it was sort of a curiosity. And a lot of people didn't really understand why it was there. And it seemed a little bit ad hoc. And so the very brief version is that the Higgs boson particle is this thing that it's a phenomenon of nature that we discovered. It really does exist at the Large Hadron Collider. But that particle itself is not the most important part of the discovery, if that makes sense. Let's back up a bit. So the Large Hadron Collider, what is it? I mean, for those that don't know, let's just do a very quick, 60 seconds description of what the Large Hadron Collider is. So the Large Hadron Collider is a 27-kilometer circular tunnel on the border of France and Switzerland, about 100 meters underground. And in this tunnel, we use superconducting magnets that we have to keep colder than outer space to accelerate 2 beams of protons in opposite directions. And we accelerate these to 99.9999991% of the speed of light. And then at 4 points on this ring, we bend these 2 beams together. We cross the streams. And the place where those 2 beams bend together, they start to collide. The protons start to collide at these very high energies. And the reason we do that is because when you do such a thing, what you're doing is you're briefly recreating the conditions of the universe as they were just a fraction of a second after the Big Bang, 13.8 billion years ago. And to be clear, we're not making a new Big Bang, but we're recreating the conditions. It's similar to, for example, if you put a saltwater aquarium in your home, you're not actually making a new ocean, but you are recreating the conditions of the ocean in a small controlled way. That's similar to what we're doing when we collide these protons at very high speeds and energies. We're briefly recreating the conditions of the Big Bang because we don't really understand what was happening back in those tiny milliseconds, not even, even smaller than milliseconds, right around the moment of the Big Bang. And if we were able to figure out and understand what was going on back then, we would help better explain the universe that we have now and could help answer some of the biggest open questions in science, such as what is dark matter? We know that there's this stuff called dark matter out there. We have no idea what it is. Why is our universe made of matter rather than antimatter? This is actually not known. It doesn't make any sense, in fact, from a symmetry perspective, why our universe would have so much matter, the stuff that makes up you and me, but would not have basically any antimatter around at all. Why is gravity so weak compared to the other forces of nature, et cetera? So these are some of the biggest questions in physics that we could possibly answer at the Large Hadron Collider with this enormous collider. And the important part about this Higgs boson discovery, though, is that, and it's actually part of why I think, I still think, of course I'm biased, but why I think that particle physics is at such an interesting juncture right now, about, 10, 12 years after the discovery of this particle, is that the way that my field actually moves forward is not in terms of, as we know, science doesn't actually move forward in terms of eureka, like a lone white male changing everything by himself, with a stroke of genius. That's not how science works. But we do know that what it does is it goes in terms of, I wonder what that is, or, I wonder what this thing means. And that's really the way that science, particle physics goes, and collider physics, the stuff that I do, moves forward. And so I know this is kind of a long-winded way of answering your question, but I'm getting there for sure, I swear. So back in the 60s, this particle was predicted. Its existence was predicted, but it kind of came about simply because everybody at the time didn't really have a way to explain a couple of other things in the theory. So if you flash back to the 60s, the 20th century was this fascinating thing that we started, at the end of the 1800s, with people understanding electricity and magnetism, and people. In fact, there was a famous physicist, I forget which one, but he gave a speech at, I think, the University of Chicago. I'm probably getting into these details wrong, but he gave a speech at the University of Chicago in like 1880 something, 1890, and he's like, yeah, well, basically all of the main points of physics have been figured out, and the rest is just details. So I wouldn't suggest anybody go into these things now. And as we know, that was completely off base. And I wonder if, I often wonder if people do things like that just because they know that they're going to end up as good stories for the future. Because then, of course, in 1905, Einstein changed everything with special relativity and Brownian motion. And then, of course, 1915 changed everything again with general relativity. And then, of course, the development of quantum mechanics. And, so all these things came together in a very, very rapid fire way in the 20th century, leading up to it all sort of started to culminate in this development of what was known as the standard model of particle physics, capital S, capital M. And it's a pretty straightforward set of mathematics that if you kind of, if you know anything about group theory and differential equations and things like this, then you can kind of, you can write down this pretty straightforward mathematics. And it almost precisely describes all of the universe at its smallest possible scales that makes up the stuff around you and me. It's like shockingly good. And at the time, this is, which we've, you might know as some of the statements of people like Wigner. I think Wigner was the one who said described or talked about the unreasonable perfection of mathematics, or something like that, the unreasonable accuracy of mathematics. Because mathematics we think of as this kind of tool to describe things, models as being this thing that are okay for certain things, but we know that they're all wrong and they all have problems. But that's true. Mathematics, for almost every other science, is a sort of a heuristic. It's kind of a rough thing to do. Except for particle physics. We have this set of mathematics and particle physics that is just absolutely like perfect. It describes everything around us almost perfectly. And at the time in the 60s, this was not yet the case. And so they had a few sort of pieces here and there, odds and ends, and specifically having to do with these things known as the W and Z bosons, which are force-carrying particles of one of the four fundamental forces of nature, known as the weak force. And at the time, they didn't really know how this happened and how this particular thing was working out. It was, it was sort of a highly mathematical thing at the time. Except somebody also noticed, well, actually, if we can solve all the problems that we have right now with the standard model, if we just throw in what's known as a scalar field. And a scalar field is, just as the name implies, it's a kind of field, a fundamental field of nature that basically takes on a numerical value everywhere in space. And this is, of course, wildly different from most of the other fields that you and I know of in physics, right? They're all vector fields, right? A vector is, of course, a mathematical object that doesn't just have a magnitude, but it has a direction. So, for example, an electric field, it doesn't make much sense for me to say that the electric field here is blah value. I have to say, no, what does it mean? How does it change as it goes in that direction versus how it goes in that direction, blah, blah, blah. So vectors, of course, are the things that we think of as when we talk about fields. But this idea of a scalar field, which is just essentially like this invisible jelly that would permeate all of space everywhere, if you throw that in, suddenly it solved everything. And so that's why at the time it was simultaneously like, Higgs and Brout and Engler and these guys are like, it was a stroke of, it was it was a stroke of of insight, definitely great insight. But also there was simultaneously, it's like, why should that be there? Like, it was sort of just ad hoc there. It turned out that it was absolutely the truth, because like I said, at the time, the importance of this thing was not so well known. It was only after the subsequent decades that it became clear how important this Higgs boson particle was. For one reason is that it was basically impossible to find. And so very different from the other particles, a lot of the other particles in the standard model. And again, the 20th century was this fascinating very unique interplay between experiment and theory, where there'd be this one, observation that would be made. And the theorists would say, well, wait a minute, if that's true, that should say XYZ and so experiment. And then you'd go out and look and see, and it was verified. And that would say, okay, that makes this other prediction. And so it had all these kind of like very precise predictions. But the Higgs boson was a total weirdo compared to that, because its existence was predicted, but its mass was not. And when you use the word mass, of course, for particles, you have to stop for a second and clarify what it is that you're talking about, because mass for particle physics is not the same word that we use colloquially, like, whoa, look at that massive building or something like that. Mass has nothing to do with volume, right? And as that's also true for macroscopic physics. But at particle level, we're actually talking about particles that, in fact, we model them as zero volume points, like an electron. An electron has a non-zero mass, this property known as mass, but it has no spatial extent. It has no volume. And that, of course, is when, our brains start to break as human beings, that as a species, we did not evolve at the quantum level. And so this notion of quantum mechanics being quote unquote weird or counterintuitive to humans that's where that starts to kick in. And we start to become incredulous about some of these things. But we know that's the case, right? We know that zero volume particles like electrons and muons and quarks, they can still carry physical properties, charge, spin, energy, momentum. And one of these properties is known as mass. And for a lot of particles, it was not known where this mass would come from. And we don't control this value of mass, right? So every electron in the universe has a rest mass that is the same. So an electron in my hand has the exact same mass as an electron in Alpha Centauri, right? We know this is the case. And so we can't control this M mass. It's fixed by nature. But what we can do as physicists is that we can potentially open up an experiment that will allow us, we can build an experiment that would allow us to potentially discover new particles that have different types of masses. And of course, this all comes down to Einstein with the famous equation, E equals mc squared. And so, of course, that M part is this thing we cannot control. What this equation says is that at the tiny particle level, there is an equivalence between energy, the concept of energy, which is the ability to do stuff, the ability to make things happen, and mass, which is this intrinsic property of an elementary particle. And so the M we can't control, but the E is the part we can control. So obviously from your high school physics, kinetic energy, right, is the energy of movement. So energy is the E part is the kinetic energy, say, of the particles that we can accelerate them to before we collide them together. And that would, because of the quantum world, when you have these two particles come together, they can in fact rearrange themselves in a particular way if the conditions are just right, which are set by nature, to rearrange in a new state, which is a new particle that might live for a tiny fraction of a second before then decaying. And so, but think about that. If we as a species have never built a collider, if there's some particle with a mass M that's way up here, I'm putting my right hand up in the air, and we as a species have only ever built a collider with an energy E that goes up to here, I'm putting my other hand at a smaller level, we'll never be able to create this particle in our experiment and to measure its properties and discover it outright. And that was the case with the Higgs boson. It was back in the 60s. In fact, there's this fantastic, and also in the 70s, there was this fantastic paper by phenomenology. It was a phenomenology paper by a bunch of theorists in the 70s, like John Ellis and Mary Gaillard, I believe. It's a really good paper about the phenomenology of the Higgs boson. And at the end, they have this paragraph where they say, we have to end the paper with an apology and a caution. We have to apologize to our experimentalist colleagues for having no idea what the mass of the Higgs boson is. But we do want you to understand, just look out for it in case it does turn up. But because of this also, we don't want to encourage any large experiments to try to find it. And so this was in the late 70s. And of course, that was just a few years before the even idea of the Large Hadron Collider came into focus. Because as what had happened is, they had started to build, for other reasons, they started to build larger and larger colliders, higher energy colliders, and the Higgs boson was never there, up to and including the big particle collider that was in the same tunnel that the LHC is in now. That was called the LEP, the LEP, the Large Electron Positron Collider. There was also, they did all of the possible Higgs discoveries or Higgs possible discovery searches back then as well. And in fact, as a side note, for me as a grad student, just before the LHC turned on in 2009, there was basically one last place where the Higgs boson could have been hiding in LEP data. And my advisor at the time, I was like a first year grad student, I didn't know what I was getting myself into. And my advisor at the time still had access to LEP data. No one was looking at it. And so we went back. And in fact, there was a non-zero chance. Again, we don't choose where the discoveries are. There was a non-zero chance we could have scooped the LHC and discovered the Higgs boson in LEP data. Obviously, that didn't happen, but it was a lot of fun for me because I learned really what it means to do experimental particle physics, as a science. But that, all that being said, that's the whole point, is like, we don't choose where the discoveries are in particle physics. What we do is we create the conditions of an experiment to make sure that if nature has a discovery waiting for us, we will not miss it. So that's what happened with the Higgs boson. Finally, with the Large Hadron Collider in, like I said, 2010, I think was when it started taking data in earnest. And after about 2 years of data, finally we started to see little hints and little inklings of a discovery, and they all came together in just the right way. And these two independent experiments, ATLAS and CMS, both designed to be complementary and to independently corroborate each other's findings. I work on ATLAS, and so we all found this. That we saw all of the hints of this particle in all the same places, which gave us confidence with this big press conference that we gave, not press conference, but a scientific conference on July 4th, 2012, gave us confidence that there really was a discovery there. So that's the particle that was discovered in 2012. But again, what that does, the most important part, as an experimentalist, that's great, because a particle, once I know how to create it, I can then study all of its possible properties. And, we can talk about this a bit more if you want, but the Higgs boson itself, in fact, could be our best. It's possible that it's our best window into the new discoveries, so-called, like the dark sector, dark matter, things like this. And we'll have to study it for a long time. But again, the most important significance of that discovery is not the particle itself. The particle itself is fascinating. It's great for me as an experimentalist. It gives me a handle of nature that I can fiddle around with, right? But the important part about this particle is that the Higgs boson is proof positive that something called the Higgs field exists, and that Higgs field is the one that they just sort of threw in to the equations back in the 60s to make everything work out. But if that's the case, that's fantastically weird. It's like, it really means that there is an invisible jelly that permeates all of space everywhere, and you don't feel it, but some of your individual particles do. And what it does is it postulates that the way that particles get mass, some of these elementary particles get their concept of mass, is that there's a little bit of their energy that is, it's zipping along through the universe. A little bit of it is dragged by this invisible jelly, and it's dragged a little bit and stuck into a point that we measure as mass. And if that's the case, that's phenomenally weird and wonderful. And it's, it's, again, the fact that it's proof positive that there's this at least one fundamental scalar field in the universe, is a complete game changer, and it was, and it's, we'll be studying this for decades to come.
I don't think. Now, there's a couple of things that I would say here. One, I don't think Eugene Wigner gets the credit that he deserves. That man predicted metallic hydrogen in like 1935, and this is cutting edge high pressure physics right now to try and figure out what the nature of it is.
Absolutely.
And whether it's metastable. And I don't think Wigner has talked about it enough. And another one that I would say in that sort of grain was John Wheeler. But that aside, the nature of dark matter may be, and you touched on this briefly, but I want to expand on it. The nature of dark matter might be as a particle. And we have some indications that weakly interacting particles exist, the neutrino. But what hope do we have with CERN as a whole, all experiments being done as a whole? Do we really have a chance of finally nailing, like we did with the Higgs boson, finally nailing the nature of dark matter?
We absolutely have a chance, but again, I have to be the extreme sort of empiricist here, because that's like I said, I think that for my field as a particle physicist, as a collider physicist, right? As again, I think my research is fascinating, and that's why I do it. I love it, and everybody, my colleagues, we do it because we love it. But I think that the Higgs boson discovery, scientifically, of course, it's fantastic and excellent and wonderful. But it also kind of did a disservice for our field, because I think it gives people the impression that my job and my colleagues' jobs, my job is to discover new particles. And in fact, that is not my job. My job is to rule out all the possible places in our data where a new discovery could be hiding. And if that's the case, what we do instead is more like cartography. We're map makers, and that's really the way that it goes. That's really what we should think of as our job. And in fact, that should not be a bad thing. That should be wonderful. That should be celebrated and shouted from the rooftops, because what it does is it recaptures the spirit of experimental exploratory science, which is really what we are and what we do. So I'm saying this because the chance that we have to discover dark matter is at this point just the same as any other experiment. And in fact, they all have to work together in concert, right? So this is in fact why, several years ago, and in fact, we've been doing this even before the LHC, but because the LHC was sort of an order of magnitude increase in the number of people working on these kinds of experiments, it started to get a lot more organized. The ability to compare the results that we get from the LHC to other experiments that are also looking for dark matter in other ways. So the chance that we have to discover dark matter is just like all the other experiments, is that we have to look everywhere. Otherwise, we'll not know whether we're missing something. And so what I mean by that is, as you pointed out there, this notion of weakly interacting particles. And so this notion of the WIMP, I think, which is what I think you're getting at. And that, of course, is dark matter is a strange concept, really, because we know for a fact that something is up, right? And we give it this name, dark matter. And so, if anybody ever comes to you and says, well, I don't believe that dark matter exists. Well, number one, belief has nothing to do with science, as far as I'm concerned. So that you're using the wrong word if you say believe. But number two, we do know that something exists like dark matter. It's just a completely, we have direct empirical proof that something is up, because we see its effects on the cosmos due to gravity, right? As we know, all of these galactic rotation curves are all often the same way. We know that we see, galactic collisions, and there's different densities of visible versus, lensing, the gravitational matter that gets lensed in a certain way. So we know that there's something up. What it actually is completely unknown. But the first the first sort of guess, which, I think is the simplest thing to do. I mean, I'm not one of these people that thinks that simplicity is a scientific principle, because it's obviously not. In fact, this was, my colleague, Steven Weinberg, we had him give a remote introductory talk at one of my workshops in Trieste a few years ago. And he said, keep in mind that simplicity is not a scientific principle, which I think is a brilliant lesson for everybody to keep in mind. But the simplest thing to do back in the day was that, okay, imagine that if dark matter exists, it is a particle. What kind of basic properties does it have to have? And they put that in there, and they noticed, okay, if it is one particle, then it should have blah, blah, blah properties. And also, there's this sort of big hint that was there, is that if it had a mass around a certain range that was in fact easily accessible at direct detection experiments and also at collider experiments like the Large Hadron Collider, this would automatically explain what we see in the universe now in terms of this dark matter densities. This is the so-called WIMP miracle, right? And again, there's nothing wrong with the WIMP miracle. It's a big hint, and you should always follow big hints, especially when they're coming strictly from empirical observations. But it turns out that, as we've done now, it's a version of cartography, right? That, there was no specific value for what this mass, for the mass of this particle should be, the dark matter. So it was really a matter of looking everywhere that you could possibly see with the experiments that we had. So they really have been doing cartography for decades in these direct detection experiments. And those ones, I think, these are the ones where, like xenon, right? Where they take an enormous vat filled with xenon and put it underneath a mountain, and let it sit there for a long time to shield out any possible sources of error or jostling. And then what that's supposed to do is that if dark matter does interact with us regular matter, it has to do so at a very, very rare, a very, very small rate. But maybe it's small enough that if we just control the conditions in just the right way, we might be able to see something like that. I mean, if dark matter exists, then you and I each have about 1 billion particles of dark matter flowing through our bodies every second at very high velocity. And so we don't have any idea what this stuff is, and it's never touched you, it's never hit you, which just means that your body is not a good dark matter detector. But maybe if we arrange things in such a way that, say xenon, very stable atom sitting there, and anything that pumps into it is most likely going to be a dark matter candidate. And so they just kind of sit there, let it sit there for a year, and that allows them, if they don't see anything, that allows them to say, okay, if dark matter exists within this mass range, then it must interact with regular matter like xenon only at a rate lower than 1 time per year, right? That doesn't mean the dark matter doesn't exist. It just means you need to maybe have a larger vat of xenon, and you have to let it sit there for 5 years instead. And that allows you to then see maybe it will finally show up. So this is the kind of game that we play in direct detection, but also at the Large Hadron Collider. Because again, there's basically 2 ways, 2 axes, 2 basic axes that we think about in directions that you can go, if you will, to discover new particles in this kind of cartography mindset. And one of them is energy with particle physics, right? So with colliders, right, like I said, with energy, E equals mc squared, if there's this particle just waiting for us to be discovered that has a high mass m, and we've never built a collider that has an energy E that goes up there, we're never going to discover it. So we need to directly. And so we need to go to larger experiments, higher energies, blah, blah, blah. But there's another direction that we could also find new discoveries at the Large Hadron Collider and, other experiments like that, which is the so-called cross-section, which is the interaction cross-section, which is the rate at which this particle is created when you collide 2 things together, like 2 protons. And again, that rate, we can't change that. That's fixed by nature, and we can only measure it. So for the Higgs boson particle, for example, at the Large Hadron Collider, we collide protons not just once or twice. We do this 40 million times a second. And we do this for weeks and months and years. And so I think that over an entire year worth of data taking at the LHC, I think, again, this is 40 million times a second with a few breaks here and there, but this is basically continuous. I think over an entire year, you only make a few tens of thousands of Higgs bosons. And if you want to do that math, that's insanely small. And so again, we don't choose that. We instead have to run the collider for a long enough amount of time so that if there is this extremely rare discovery waiting for us, it will finally show up in our data. And that's the same case. That's the same thing we can do with dark matter. So there are various ways that we can make dark matter at the LHC. But again, when you collide 2 protons together, something can happen deep down inside. The thing that we're really good at the Large Hadron Collider is not necessarily making a dark matter particle itself. We can do this, but the best sort of, again, well-motivated, I don't like to use that phrase very often, but the kind of the ranges of the mass of this particle of dark matter are in the so-called, kind of GeV range, right? And we can do this at the Large Hadron Collider, but this is a rather sort of small mass particle for us to be able to discover. The thing that we're good at, though, at the Large Hadron Collider is creating, coaxing into existence these high mass force carrying particles, such as the Z boson, right? Or the Higgs boson is not necessarily a force carrier, but it is a scalar particle. And so we can make these high mass particles. That's important because that allows us to say something very direct about dark matter, but also the so-called dark sector. Because, like I said, this WIMP miracle is really in tension. The WIMP paradigm is in tension because we have been looking for this for decades, and we have not seen any WIMPs at all. And so it doesn't mean that WIMP was a bad idea. It just means that that's possibly not the way that dark matter exists in the universe. And so it's possible that, in fact, that the so-called dark sector is not just one particle. In fact, it kind of makes no sense that it would just be one particle, because there's something like 5 or 6 times more dark matter in the universe than there is you and me matter. Why would we assume? And you and me matter is actually really weird and baroque and complex. Like, we have this strange, the standard model of particle physics has this bizarre sort of, gauge group SU3 cross SU2 cross U1. It's very strange. And the symmetry is broken in just the right way to give these masses. Why would we assume that 6 times the matter of the universe is less complex than that? So if you you postulate this, then there could be some extra particles in the so-called dark sector. And at the end of the day, though, if those particles have no way of talking to or interacting with you and me matter, then we're kind of dead. Because if the only way that dark matter interacts in the universe is via gravity, we're kind of screwed, because we can't. It's very hard for us to do precision measurements with gravity. And I'm not talking about gravitational waves. That's a very precise experiment. But to be able to use gravity as a tool to make very precise measurements down to the level of what we think a dark matter particle mass should be is basically going to be impossible to do. So what we do is we assume, okay, if dark matter exists, if this dark sector exists, there has to be some sort of way that it talks to the standard model. And this talk to, quote unquote, takes the form of these so-called force carrying particles. And so as you know, the three of the four forces of nature, the fundamental forces, are mediated. They proceed via the exchange of other kinds of particles. So for example, an electron and a positron, they zap each other by exchanging a photon, right? And a photon is the force carrying particle of electromagnetism. And then the weak force, as we mentioned earlier, is kind of a strange one. It has three different force carrying particles, the Z and the W plus and the W minus. And then of course, in the strong force, the force carrying particle is known as the gluon. So if dark matter exists, and it does, and again, that's just sort of it's not a hope, it's just a good idea. If it does talk to or interact with standard model particles in some way, then it will do so probably via a new force carrying particle. So this would be like a dark Z boson or a dark photon, something like that. And if that's the case, we at the LHC can say something directly about those kinds of things. Sometimes you'll hear them referred to as mediators, right? Because they mediate the interaction between the dark sector and the standard model sector. So we have been looking for these kinds of, this is part of our bread and butter. This is part of our menu of searches that we're doing all the time. Because as more data comes in, it takes time to collect it and make sure it's working and it's been collected well. And then it takes a much longer time to analyze it and write papers about what we see. And then once you put out those papers about different dark photons or dark matter particles, then you can start to compare those results, those exclusion results, with the results that we get from the direct detection experiments and also indirect detection experiments, where for example, you put a satellite up in the space, where you put a satellite up in space and wait for particles to hit it and see if you see a larger percentage of them coming from some direction that could indicate, an enhanced collision rate that could be dark matter, something like that. So we start to put these things all together in this cartography way. And, I can't show you the plot right here, but if somebody wants to, your audience can look it up, and they can look up these dark matter exclusion plots from the LHC. And you can see that we're really cutting into a large amount of parameter space, mass space, the possible masses of these particles, but also extremely rare interaction rates that at some point we're going to, this is the sort of like diminished returns that you really just have to kind of convince yourself, the community has to convince itself that if we run the collider, at the Large Hadron Collider, right? This is why it's such an interesting moment right now, because we've kind of shifted our mindset away from, particle hunter, Higgs hunter, supersymmetry hunter, toward this more cartography mindset. And we're going to take data for something like, 15, 20 more years. So there's still a large, and right now we've only taken about, I forget what it is, 5 to 10% of all of the data we will eventually collect. So there's still lots of time for a discovery to show up if it is there. And this could be anything, because this could be a dark matter particle, it could be a dark photon, it could be supersymmetry particles, it could be exotic Higgs bosons, evidence of other scalar fields, fundamental scalar fields in the universe, etc. So all this stuff is what we, is on the menu. And it's just this menu that will continue to be chipped away at for 15 to 20 years in this cartography way. And so, that's the kind of, again, the long way of answering it. We absolutely have a chance, but again, we don't choose that. And in fact, that's a glorious thing. It's our job to make sure that we have looked everywhere in our data. Oh, then, like I said, because at some point, have to say to yourself, okay, well, how much more do we think we could squeeze out of this existing machine, right? If we run it, and as you know, a lot of processes in physics they go by an exponential or logarithmic way, right? So you can imagine that we get a lot out that we can out of this machine for, say, 20 to 30 years worth of running. But then we wouldn't get much more out of 10 more years. We would get a lot out of 100 years, but we wouldn't necessarily get a lot out of 10 more years. And so you start to think, okay, should we start to build another machine? Should we shift over toward a larger energy machine that allows us to get this jump up in energy that we have not been looking at for a long time? And that's the idea for this so-called future circular collider, which is proposed to be about 100 kilometers around Geneva. And so that's what, so when you say, is there a chance to discover dark matter? There's absolutely a chance. But again, we don't choose where that discovery is. And it's basically impossible for anybody right now to put odds on this. And I think you can bet on everything on the internet. I'm not a betting person myself, but I think you can bet on anything. There's probably some odds that people are giving on dark matter. If you want to go and bet on that, you can, but understand those odds are based upon absolutely nothing in terms of science.
Now, the future of particle physics and particle accelerators, there's that, but it can scale up from even there. So let's say 500 years from now, spacefaring humanity, could we build a solar system-sized particle collider?
So I think you did your homework here, because you're talking to the absolutely right person about this. This is one of my obsessions. So yeah, this idea, right, is that, like I said, one of the axes, one of the ways that we can make sure that we're not missing discoveries is along the energy axis, yeah? And so this energy, again, opens up the possibility that if there is a new particle out there waiting for us with a high mass m, and we've only ever built a collider with energy E that goes up to something smaller than that, we'll never be able to discover it. So we need to do that. We need to, the so-called energy frontier, but the very high energy frontier too, because that's the thing that's fascinating. That's the interesting. That's what I think is why this moment right now is arguably one of the most interesting moments in physics history. Because the history of the 20th century was really, like I said, it was this wonderful interplay between theory and experiment that led to all of these sort of discoveries by clockwork. And it was always proceeding basically more or less by big sort of fuzzy hints, if you will, sort of big fat hints. We don't have any hints anymore. Like, we have no hints. There's no big hint anymore. And to the point that, like, it actually, I think for some of my, more venerated colleagues, it's like, I think it throws them for a loop, because there's no big hints anymore. They're always just sitting there. In fact, the Higgs boson, there was a pretty big hint even before the LHC turned on. Like I said, the Higgs boson mass itself was not predicted by our standard model theory, but the mass itself doesn't exist in a total theoretical and observational vacuum, if that makes sense. The mass is a little bit dependent upon some other values within the standard model, such as, the mass of the top quark, which we know, and the W and Z masses, and particular values of this thing called Q weak, et cetera, that we can measure. So if you put all these things together before the LHC turned on, you can almost kind of triangulate, and you can start to say, okay, well, it would make sense if the Higgs boson exists and it's within this blah, blah, blah mass range. This would make a lot of sense with what we already see with these other so-called electroweak properties. And at the time, before the LHC turned on, in fact, they predicted the sort of the mass of based upon these fits, again, which are not first principles, they're experimental fits. They predicted a mass of the Higgs boson that was still a little bit within the range of LEP, when we obviously didn't see the Higgs at LEP. So that made people think it's a little bit weird. But it turns out that the place where we found the Higgs boson at the LHC, at the Large Hadron Collider, was not too far away from what that original electroweak fit prediction was. It was, a couple of 2 or 3 sigma or something like that away, which is totally okay. So in fact, it was pretty low mass compared to what the LHC can look for, very, very high TeV scale, tera electron volt scale particles. But the Higgs boson is 125 GeV. And that was very well within the sort of electroweak fit range of plausibility. So that was one example of how you have to sort of, it wasn't a guaranteed discovery, but it was a big fat hint. And there it was. We are completely out of hints, but we have enormous questions still to answer. And that's why we have to, that's why this notion of changing our mindset, both within the field and for those of us that talk to the public a lot and that like to engage with non-specialists, to let them know that this is the way it's always been. We just had sort of a lucky century, and we really need to recapture this spirit of exploration and experimental science. So the next sort of plan to discover, really the job of physics, like I said, collider physics, physics is to map out all the possible places where a new discovery could be hiding. And that means that if we don't have a new guaranteed discovery between here and something extremely high, known as the Planck energy, which is, I think, is what you're getting at, if we don't have any hints as to big hints as to where the discovery could be, we really have to just build successively larger colliders to sample these energies until we get up to, either rule out things or finally get up to the Planck energy. And so that's why, I have been thinking about this for a long time. This the sort of proposed next generation collider would be, like I said, something called the Future Circular Collider. Presumably when the future becomes the present, we'll change the name. But instead of 27 kilometers around, which is the Large Hadron Collider, this thing, the FCC, would be 100 kilometers around and would enable us to reach collision energies. There's something like 7 times what we can currently do. That's amazing. That's a huge step forward, and it absolutely has to be done, because if we don't look there, we'll never know what discoveries are waiting for us. However, simultaneously, and two things can be true at the same time, the FCC is a great idea. Simultaneously, there's nothing magic about that energy range. There's really not. There's no sort of guaranteed discovery that we will make. And in fact, there's nothing magic about any energy range up to and including the Planck energy, maybe 3 orders of magnitude below that. So the Planck energy, which I think you know about, the Planck energy, in fact, is the next guaranteed discovery in particle physics. And I think this is kind of what you're getting at, because it's also one of my biggest, obsessions. And in fact, to back up a bit, we do need to go to larger and larger colliders to get to higher and higher energies, like I said, to sample higher energies, just to see what's there. And again, we'll never know unless we look. So, and every time we write a paper that technically says, no, we did not discover a particle in the search, that's actually brand new information about the universe that we did not have before. We're measuring the standard model in the absence of new discoveries. We're measuring parts of it where we've never looked in the history of humanity. So this is all brand new information about the universe. But beyond the FCC, we need to be thinking about that as well. And so I, in fact, published a paper, I guess a year and a half ago or something now, 2 years ago, with a colleague of mine, Frank Zimmerman, one of the world experts in accelerator physics. I'm more of a detector experimentalist, physics thinker, and then he's more of an acceleration physics guy. And so we wrote a paper, in fact, about the prospect of building a particle collider that circles around the moon, a circumference of a great circle of the moon, sometime in the 22nd century. And this, based upon our paper, there's actually no showstoppers for doing such a thing. All the technology either exists or is basically going to exist in the next few decades. And it's just a matter of, scaling up, and putting resources toward it. So, the idea is that this would give us a jump up in energy of 1,000 times, right? And so this would be something enormously high. But in fact, it's still not a guaranteed discovery. There's no guaranteed discovery in something like a moon-based a circular collider on the moon. We called it the CCM. And there's no guaranteed discovery there either. In fact, the next guaranteed discovery in particle physics is, again, at this thing called the Planck scale. And the Planck scale was, as its name implies, Max Planck, fantastic physicist, back in the day, he was sort of looking at these fundamental constants of nature, which things like the quantum mechanical constant H, or sometimes referred to as H bar, and the gravitational constant, and the electron charge, and the speed of light. And in fact, these numbers are all just kind of put there by nature, and we don't really have any real a priori explanation as to why those numbers are what they are. For example, the electron charge, okay, it has a value that you can put down in various units, but why that exact number? There's no real reason why it's there. There's no mechanism that would lead to that number, right? So, but if you look at these particular constants of nature and put them together in just the right way, Planck noticed that you could make certain types of values that have units of things like energy or time or length and or mass and things like this. And these values are the ones where, for example, you have H bar and you have gravity coming together. So quantum mechanics and gravity coming together. This is one of the biggest open questions of science, which is how do quantum mechanics and general relativity work together, if at all? Because we have no idea if they do. We have a good candidate for how they could, but there's no way to currently test it unless you could build a collider that got to up around the Planck energy. However, the Planck energy is not 7 times the Large Hadron Collider. It's not 1,000 times the Large Hadron Collider on the moon. It's actually 10 to the power 16 TeV compared to the Large Hadron Collider 13 TeV, tera electron. This is 16 orders of magnitude. And by some calculations, as you're implying, to be able to create a particle collider, to construct something that would reach the Planck energy, we would need to build a circular collider like the Large Hadron Collider, but one that circles around, say, the outer orbit of Neptune. So clearly, this is not going to happen anytime soon in our lifetimes. 500 years, I think that even a solar system collider is not really going to happen within 500 years. I think that's beyond the scope of even 500 years. However, the good news that I'm here to bring to you personally, because again, like I said, this is a personal obsession of mine, is Frank and I and Frank did the calculation first, and then in fact, this is the sort of spoiler I'll give you a teaser. Frank and I, in fact, are working on a paper right now about the possibility of building a Planck scale collider. And it turns out that you probably would not need to build one that circles around the solar system. You would probably only need to build one that circles around the sun at about a radius of 1/10 of the distance between the Earth and the surface of the sun. So much smaller than the orbit of Neptune, for example, but also rather still outside the realm of our civilization. 500 years, I think we definitely could get something around the sun, this 1/10 of a distance between the Earth and the surface of the sun. Solar system, I'm not so sure. And in terms of timelines for such a thing, it's really hard to say. I think that just because of the way that things are kind of progressing with respect to, one of the reasons why we even proposed the idea of a circular collider on the moon was not because the moon is some sort of magic, large object. You have obviously noticed that the moon is smaller than the Earth. You could fit an 11,000 kilometer circle somewhere on the Earth. But on Earth, of course, you have humans that live there in places, and there's enormous topographical issues and drilling issues and things like that. So we thought that since there are a lot of entities that are both public and private that are very directed and focused on going back to the moon, it's both scientifically interesting to think about using the moon for such a project, but also I think for me, it's a kind of existential necessity for humans to remind ourselves that we should not only do things. For example, I think that we're sort of on the verge of just giving space, the moon and Mars to wealthy private individuals and corporations whose only interests are extraction, exploitation, and profit. I think this is a bad thing because this kind of mindset has led to the devastation of the environment due to anthropogenic global warming here on Earth. So I think that if we were to sort of head this off at the pass with big science experiments that are strictly for the public good, for public curiosity, like a circular collider on the moon, or it doesn't have to be that. My astronomer colleagues have proposed things like, fantastic telescopes on the far side of the moon to be radio quiet, things like this. If we have these experiments in mind, then it will remind people that the moon is supposed to belong to everyone. So I think that there's nothing magic about this circular collider on the moon. I think that could definitely happen in the next, say, 150 years. But this notion of a Planck scale collider, again, I look forward to being able to talk about this more once the paper's out in the next, say, 3 or 4 months. But it's hard to put a timeline on being able to build something that circles around the sun. There are some ideas you could think about as how to do this in a realistic way. Like, for example, I think that just because there's a lot of, like I said, I speak around the world at these events, and sometimes I've been talking about this even before we wrote the paper. I've been talking about the idea of a circular collider on the moon in a kind of rough or inspirational way, if you will, right? You're talking to a public audience and really get people sort of jazzed up and like, wow, gee whiz, a collider on the moon, cool. But then I finally put it in a paper, and it turns out this could totally happen. And I very often get people that come up to me afterwards the talks and like, yeah. In fact, one time I was giving a talk I forget where it was, and some guy came up after me. He's like, "Hey, so this particle collider on the moon, do you have to build it on the moon?" And I said, "Well, no, you don't have to. He's like, "Could you build it in space?" And I'm like, "Well, yeah, for sure you could." And he's like, because I'm an investor. I'm an investor in asteroid mining. So I was thinking that if you just go to the asteroid and start to dismantle the asteroid, then you could make the collider in space. And that's, in fact, a fantastic idea. So I think that, for example, a collider around the sun, one of the ideas that we are investigating for the paper is that you could, for example, dismantle Mercury, and you could reconstruct Mercury into a series of, roughly, it has an elliptical orbit now, but you could turn it into a circular orbit collider that you would need roughly circular for a collider like that. And before you start to freak out about, getting rid of Mercury, in fact, I consulted with my celestial mechanics colleagues, a close colleague of mine, even from undergrad days named Konstantin Batygin at Caltech, and he assured me that dismantling Mercury would actually not affect the stability of the solar system in any appreciable way. So, yes, I think maybe it's interesting to take stock for a moment and see that I have actually come to your show and I'm suggesting that we dismantle Mercury to build an enormous particle collider around the sun to reach the Planck energy to make miniature black holes to see what quantum gravity is. Yeah, I think I said that.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.